All right. Good morning, everyone, or I guess good afternoon. My name is Samuel Beiler. I'm from the University of Toledo in my 5th year, and I'm going to be presenting work that I've done along with this collaboration of fine people on probing the fundamental properties of ultra-cold dwarfs in the era of JWST. So first off, I'm going to find what I'm going to be talking about when I say fundamental properties for this talk and how we derive those. So first off, we have bolometric flux, which we can calculate from broad wavelength spectral energy distributions. We also have distance, which we can calculate from precise astrometry. And we have radius, which we can get from eclipsing spectroscopic binaries. All of these fundamental parameters can also get us derived parameters, such as bolometric luminosity and effective temperature. And these are things that are all common measurements for your stellar objects and any substellar objects, but it's particularly difficult to get substellar fundamental properties. And the reason for that is, as Jackie alluded to, we have no main sequence for brown dwarfs. Brown dwarfs cools the age, and so we don't have a mass luminosity function. We have a mass age luminosity function. Along with that, they're difficult to observe because they're these cold temperatures. They're dim and are red, emitting mostly in the near infrared, making them harder to get from the ground. And we also have very few observed radii or masses for these substellar objects because substellar binaries are fairly rare. And so in this talk, we're mostly going to be looking at the flux to luminosity to temperature pipeline. And in that space, we have previous work that's gotten us good M, L's, and T effective temperature measurements, but we've had some issues getting the colder objects. And to go colder, we need broad wavelength SEDs, and for that, we need James Webb. So we put in a James Webb cycle 1 proposal. We asked for 75 hours to look at 24 late T and Y dwarfs. To show you what that looks like, we have a 400 Kelvin model plotted in gray, which we then convolve down to the near spec prism and MIRI LRS resolutions. And we're looking to get 0.6 to 12 microns of spectra, and then getting 4 photometric points at 10, 15, 18, and 21 microns, the last 3 of which extend our SED out to 23 microns, and the 10 micron photometric point we use to calibrate the MIRI LRS data. So with this proposal, our main goals were to first obtain a representative sample of broad wavelength SEDs so we could calculate bolometric flux and bolometric luminosity, and then to calculate effective temperature using that bolometric luminosity and previously collected parallaxes to get effective temperatures with 5% precision for their full sample using radii derived from evolutionary models, and using these luminosities and temperatures to infer and anchor the cold end of the substellar mass function. So in this talk, I'm going to be focusing primarily on those first 2 topics. And when we're talking about obtaining a representative sample, to do that, we're looking at objects that are later than T5, because we're trying to probe that cold end of the spectrum. And we're looking within 20 parsecs, 1, because that's where most of our white dwarfs are, and 2, because we want a volume limited sample for that mass function step. Because we want to be representative, we're including no binaries and no suspected subdwarfs. And we also, because we want those precise bolometric luminosities, we want a parallax fractional uncertainty below 5%. And so we have 140 objects then left, which we separate out into 8 bins in 4.5 magnitude space. And then in color space, 3.6 minus 4.5, we take for each bin one that has an average color, one that is slightly redder, and one that is slightly bluer to get us our representative sample. So I'm going to talk through what our process looks like using one object. This is WISE 1541 minus 22, and this is the data we had before James Webb. We had ground-based or Hubble-based near-infrared data, the WISE and Spitzer photometric points, and then some of our objects had M-band data taken from the ground, and some of our early Ts also had Spitzer IRS data out to 12 microns. But that's what we had before James Webb, and now this is what we have with James Webb. We have all the important CNO molecules. We've got methane, water, CO2, and CO, and we also have really beautiful ammonia features, including an ammonia feature at 3 microns, which is the first time we've seen a clear observable ammonia detection in the near infrared. So I want to talk specifically though about 2 parts of the spectrum. First off, this place that I'm calling the 5 micron peak. And the reason we're looking here is because this contains a lot of the carbon chemistry that we're looking at. We have strong CO2 absorption there in red. We have strong CO absorption there in pink. And then we have the methane, which is giving us the red edge of this 5-micron peak. And we also, as an added bonus, get water giving us the the red edge of this peak. Flip the red and blue for the methane and water. So we have this beautiful portion of the spectrum that's telling us a lot about the physics and chemistry. And then looking back here, also from 8 to 12 microns, we have this beautiful forest of ammonia features. We have the R and Q rings of the ammonia feature, and this beautiful Q branch doublet there in the center. And this is the first time we're really seeing this in detail and going into these colder objects to get those really strong R and P wings. So we have this beautiful spectrum with a lot of molecules able to be seen. What we really want is the fundamental parameters. So this is now plotted in F lambda space. And to get F bowl, we need a SED from 0 to infinity. So we linearly interpolate from 0 to our spectrum, and then linearly interpolate through our photometric points, and then drop Rayleigh Jean's tail at the end. We can then integrate under this in F lambda space to give us our bolometric flux, which using distances from Davy Kirkpatrick's 2021 paper, we're able to get bolometric luminosity to extreme precision. And if we knew our radius, we'd be able to get effective temperature. Unfortunately, as I said, we don't have observed radii for many brown dwarfs. And so instead, we need to make some assumption. Luckily for us, brown dwarfs are all roughly 1 Jupiter radii plus or minus 10%. And so if we assume 1 Jupiter radius, we get an effective temperature of 421 Kelvin. But we'd like to make a better estimate. And to do that, we're going to use the evolutionary models. So here is a grid from the Sonora Bobcat models with luminosity, age, and radius as our 3 parameters. We just measured our luminosity, so we know that distribution. And if we assume some age distribution, we can then draw a bunch of points and get a radius distribution. And so we show that here with 2 different age distributions. In blue, we have a uniform age distribution from 1 to 10 gigayears. And we make this assumption because all of our objects are field objects, so they don't have a known age. They don't have an age associated with them. We also look at an exponential age distribution, which was published in Wilbest's 2024 paper that favors younger objects and thus larger radii objects. The exponential distribution does extend down to 10 gigayears. It is just being overlapped by the uniform distribution. But with these randomly drawn points, we get this radius distribution shown here, with the blue being the uniform and the purple being the exponential age distribution. And so we see some disparity, but the average is actually pretty close, with the dashed lines being the mean value for each distribution, and in red being the 1 Jupiter radii as a reference point. And so with this radius distribution, we then take a luminosity to get a temperature distribution, shown here, again, with the dashed lines being the mean value for each of the distributions, and the red being the temperature, assuming 1 Jupiter radii. And so we're getting about 420 Kelvin for these objects, which falls within 1 sigma of the estimate from Davy Kirkpatrick's 2021 paper. But we're going from over a 20% error down below a 3% error. So a huge increase in precision and accuracy for these. So that's for 1 object. We then repeat this process for all our objects and attach it to the previous work from Filipazzo 2015. And you can see that we're probing much dimmer in H-band magnitude and 4.5 magnitude. We're getting temperatures ranging from about 1,000 Kelvin for T6, all the way down to 360 Kelvin for coldest white dwarfs. But one thing you can also see from this plot that I find very interesting is that there's a lot of space given off in our magnitude space, but it's all being crunched together in spectral type space. So the spectral types sort of belie the amount of diversity we have in these objects. And we can see that by looking at a spectral sequence. We go from T6 all the way down to Y1 here, skipping T7 because we don't happen to have any T7s in our sample. And with the sequence, you can see how the near-infrared just disappears as we go colder and colder, as the black body shifts redward, and the water and methane absorption increases in strength. We also see the ammonia increasing in strength as we're going deeper, and we see the CO2 and CO getting weaker and weaker as we go lower. I should say that on the left is things plotted in absolute flux space. On the right, it is plotted normalized to 4.2 microns. They're the same plot. Essentially, the one is stretched for the hot objects, and this one is stretched for the cold objects. So you can get a sense of the features in both of them. But even with this diversity, we have so much diversity, and that's because even similar objects are very diverse. So here we have 3 different objects. WISO 535, WISO 430, and WISO 1541. The two objects up top, the red and blue, are basically the same temperature, and the black object is about 100 Kelvin cooler. And you'll see that the two objects that are basically the same temperature don't match anywhere in their spectra. They look completely different. And similarly, if we look at the near infrared, we have the red and the black spectra look pretty similar, and then don't look anything alike anywhere else, and also have that 100 Kelvin difference. And similarly, 8 to 12 microns, similar for the black and blue spectra, but matching nowhere else. And here at the 5 micron peak, they're so wildly different. And that's because this 5 micron peak is strongly impacted by gravity, by metallicity, by C to O, and disequilibrium chemistry. So here's the temperature sequence of our objects, and you see that once we get to like 600 Kelvin, we just get absolutely no sequence. So we have objects like 1047 with this whoppingly deep CO2 and CO. We also have objects like 0535, which have basically no absorption in CO2 and CO. So there's a lot of diversity here. And that means there's a lot of physics and chemistry for us to entangle in this region of the spectrum. And one way we've started going after that is by looking at how models fit to these spectra. And so if we look here, one thing we've been seeing is that we aren't seeing phosphine absorption in our spectra like the models have been predicting. And so to show that, we have the alpha models in purple. And you can see we have 3 of our objects and 1 object published by Adam Berghasser, Uncover BD3. And you can see that we get this whopping phosphine absorption for a bunch of these that we aren't seeing in the spectra. However, they're giving us a sort of divot that needs to be there that isn't being included in the models because the models don't have enough CO2. That's especially clear in these 2 diagonal objects in 2056 and 0359. And to test that and to sort of show that's the case, we took the ELF-OWL models, we took their PT profiles and chemical profiles, and added in 2 parameters to modify their phosphine and CO2 abundances. And what we find is that we need over a factor of 100 increase in CO2 to get good fits to the models, and a drop of at least a half for our colder objects. If we look at 2102, you'll see that we don't need a phosphine drop there, and that's because there just isn't phosphine in the original fit to the model. But so we're learning a lot about the physics of these objects from these broadband James Webb SEDs, and we're getting really precise fundamental parameters, and eventually we'll be able to probe at the substellar mass function of these objects. Thank you very much.
Okay, so we have 3 minutes for any questions. We have folks running the mics around.
You just want to yell it to me and I'll repeat it. Oh, there we go.
All right. Elliot Riley, that's Smith College and also Recon. You mentioned at the very beginning eliminating binaries from the samples. I am super curious how you go about that, especially for.
So we were basing off of the Kirkpatrick 2021, where he listed out a bunch of suspected binaries. And so we're just trimming all of that sample, those things that in the literature have been proposed to be binaries. Oh. Yes, Davey would be the better person to ask about that specific detail.
Yeah, we have time for at least 1 more question. If we go to Jonathan over there in the back, and then maybe Sandy for the last one.
Hey, really great talk. Thanks. I was just curious, what temperature are you choosing for the Raleigh gene set, and does it matter much?
We're choosing to, so we have the Raleigh genes tail, and we have some constant proportionality of the constant of the Raleigh genes tail divided by lambda over 4. And we solve for that constant based on the last photometric point. Yeah, correct. And we're using a Monte Carlo simulation to wiggle that. So we're getting errors on the Raleigh genes tail as well. Yeah, We've currently put off fitting to atmospheric models at this point, just because we have so much other stuff we're working with. And for the paper where we talked about phosphine and CO2, we were looking specifically at if we treat phosphine as if it's in disequilibrium chemistry, then how does that change things? Because if we just are changing phosphine without understanding of why it's different, like there has to be some physical reason we're doing that. And so probing into that is really what we were more so looking for.
Yeah, thanks a lot, Sam.
Right.
That was really great.